Over the next couple videos, we're going to look at the idea of dimension reduction. And just a note, we're assuming you know no linear algebra when we do dimension reduction. So we're going to do a lot of hand waving because dimension reduction is linear algebra. And if you don't have that background, we'll just skim over the very basics so we can use it in our machine learning. So when it comes to dimension reduction, what we're doing is identifying the combination of attributes or principal components or directions in the feature space that account for the most variance in the data. So ultimately what we're doing is we have all these variables that we are using to label data or find clusters. And so whether we're doing classification models or whether we're doing cluster analysis, we can do dimension reduction. And what we're doing is we're taking all of the variables and saying some of these variables tell us the same information as other variables. Okay, so there's this correlation between them. In which case, we don't need both variables. Maybe we need a little bit of one variable and a little bit of another. And so we can actually kind of create this formula that is a combination of the two variables that captures the variability in the data. So we're reducing the dimensions. We don't need as many different variables because we're creating these basically formulas from the existing variables, these new forms of them that summarize all the variability in the data. That's what dimension reduction is. There are linear methods for dimension reduction called principal component analysis and singular value decomposition. There are also nonlinear methods. There's two that we're going to talk about that are called manifold learning. One that is an isomap and the other one is called LLE. And then we have something called T-distributed stochastic neighbor embedding. So we'll go through all those in the next couple videos, but we'll start now with the basics of the principal component analysis. So with principal component analysis, we're identifying the direction in which variables vary. So not only are we trying to find, is there a way to collapse the variables down, but we also look at the direction that they vary in. Right? So we're looking at directionality when we do principal component analysis, so that's important to know. And then what we're doing is creating a covariance matrix. So we look at covariance when one variable changes, how much does the other variable change? And then we're using what is called eigenvalue decomposition that looks at the direction of the change to find those principal components. So we look at how much change in one variable predicts change in another variable, which direction those changes are happening in order to simplify the space down. The principal components are the ones that have those largest eigenvalues, right? That explain the most amount of the variability. Now, since the principal component analysis considers how much variables move relative to another variable, we're going to have to standardize all these variables. So we're looking at it on the same scale. So what we're going to do is with principal component analysis is the key is to figure out if we have a bunch of variables, how many components in this simplified space do we need to explain the data? So the preferred number of components is going to be the one that preserves much of the data structure so that it's trustworthy. So we need to explain about 90 to 95% of the variability in the data. But remember, what we're doing is not deciding which variables to keep and drop, but we're actually creating new variables that are kind of a little bit of multiple variables, recognizing that there's correlation or relationships between these variables. And so some of them provide the same information about the data set. Now, when we are trying to decide how many components to use, if the dimension reduction we're doing is paired with cluster analysis or a classification model, then typically the number of components is going to be the number of clusters or labels. So we're going to look as we do our principal component analysis, how do you pick the number of components? But recognize that when you often apply this with cluster analysis or classification, it's the same number of components in your principal components as it is the number of clusters or classification labels that you have. All right, so let's take a look at PCA. When it comes to principal component analysis, there are different versions, and we'll look at those in the next video. there is what is called incremental PCA. We use this if we have a really large data set, and so we're adding the data in batches in order to identify those principal components. We can't analyze all the variables and all the data simultaneously, so we're doing it in chunks. And we also have what is called sparse PCA. This is where it is acceptable to ignore some of the variables when creating these new combinations of variables. Because those variables don't add as much, they're being covered by other variables. We're going to use that sparse PCA, for example, when we are looking at images. There's a lot of detail, a lot of variables in a very simple drawing, as we'll see in a couple minutes. But sometimes there's a section of the picture that's always blank, in which case we have a sparse matrix. We have sections of the data set where we expect to have no information, and so it's acceptable to ignore some of that, some of the variables tied to that particular portion of the image that's always absent any recognizable features. And then we have kernel PCA. Kernel PCA is used when the variables have a nonlinear relationship. So if we have a relationship between variables, for example, years of membership and the yearly amount they spend, maybe that's not a linear relationship. It doesn't just go up equally over time. Maybe initially they don't buy a lot, and then the longer they've been here, it goes up quite quickly, and so we get this kind of exponential growth. Or maybe there's some kind of diminishing rate. Our customers buy a lot from us initially. Now they have one of everything we sell, and so that rate is not a linear decrease, but it decays quite rapidly once they've exhausted our products. Maybe it's not something you continually buy over time. So if your variables have a relationship that's not a linear relationship, then you can use the kernel PCA. Again, when it comes to nonlinear methods, often used with images, and we'll talk more about that when we're looking at recognizing images. Then we'll use more nonlinear methods like manifold learning, isomap, and LLE, and the t-distributed stochastic neighbor embedding. All right, let's take a look at PCA. All right, so let's go in. Just a reminder, you can find the workbooks here at drstephpowers.github.io/BIA. You'll find the dimension reduction Python notebook here under chapter 9, where we're looking at predictive analytics, what is going to happen. And that's because when we do our dimension reduction, we're often tying it to something like cluster analysis, where we're looking at what do we expect to see? Can we identify groups of people, of events? And if we can identify their group, then they're more likely to behave a certain way. In our dimension reduction methods, we're going to look at some image recognition. So as we use this to identify images, then if we can identify what it is, then that's going to help us identify what is likely to happen. So these methods, of course, aren't strictly tied to the type of analytics. We have just kind of put placeholders where we're using them for that particular approach. All right, so go here to dimension reduction. In this particular data set, we're using a couple different data sets. So we have our bargain numeric, which is our data set that is our survey to prepare for collective bargaining of our union members. We have the e-commerce data set from Kaggle that looks at how much people use our app and our website. And then we're going to also do this one here called Fashion and NIST, which is also from Kaggle. And this one is going to look at some images, pictures of clothes. And so we're going to be identifying pictures of clothing. All right, so if you are going to be doing this workbook, make sure you download these files, stick them into your Google Drive, open this in Google Colab, log into your Google Drive, mount your Google Drive, and load in your data sets. All right, so let's go in. So I have imported pandas as PD and imported numpy as NP. I have linked this to my Google Drive. I've loaded it in my Google Drive in a folder called BIBA Handbook, Chapter 4 and Chapter 9. And so I'm importing in my data sets here. We're going to start with the e-commerce data set that we were using in the cluster analysis. And so let's just load in our e-commerce data set. All right, so ecom here, and then ecom.head, we're just looking at the summary table. Here we go. All right, so this data set has information: email, address, the people's online avatar, average session length, time on app, time on website, length of membership, yearly amount spent. And so what we want to do is look at using principal component analysis for this information. Well, when we do our principal component analysis, we're applying it here to our interval ratio data. So we are going to exclude these first three columns. So what we can do is we can look at here, describes, summarizes those interval ratio columns here. We can see the average session length, the average time on the app, the average time on the website, and so on. The idea here is that our data has variability, right? So the session's length vary, the time on the apps vary, the time on the website varies, the length of membership varies. And so if we're using principal component analysis, the variability that's in this table, we're trying to maintain it without having to keep all of these variables as they are. So essentially what we're looking at is, can we combine these variables using essentially linear algebra to create this new variable that identifies some of the movement and range in these without having to have all of this. Now, this particular data set's not particularly cumbersome or huge, so you don't really need principal component analysis, but we'll start with the smaller data sets so that I can see how this works before you start dumping in the big giant ones. All right, so to do principal component analysis, we're going to import PCA from sklearn.decomposition. And we are going to, because we have different variability in these different variables, we are going to have to standardize. So we're going to use that sklearn.preprocessing. We're going to import standard scalar. All right, now we're going to take that original data table, and what we're going to do is we are going to get rid of those first couple columns, email, address, and avatar. So this is 0, 1, 2. So we're going to start at the index column 3 and forward to just capture the information that we need. So we're going to do ecom, and then from that ecom columns 3 and on. And so that's what this command is here. And so we can then, you can see here, if I do ecom.head, you can see there's our data. And then we can use that standard scalar because we can apply it to the entire table here. Everything can be standardized in this table. We'll do scalar equals standard scalar with our little parentheses around it, and then we'll fit and transform to the whole data table. So we now have scaled data. So now if we look at our table, scale, yeah, I was gonna say. So you'll recall before when we talked about when do we use the standard scalar versus not. We use the standard scalar, this built-in package, if we want it in an array. So that's what you have here, right? You have this array. We didn't use it and created our own program. Well, my mind is not working. We created our own we defined our own little function. There we go. When we wanted to apply it to each row, we wanted to maintain that data frame and keep it as a table. So here, because we're okay with it being an array, we'll apply it to the table, but recognize that it's going to convert it into an array. All right, so now that we have our data in an array that's been standardized, we're going to do our PCA. So PCA, and then we define the number of components. We're going to define the number of components here, and then we are going to look at whether or not that's the appropriate number of components. If we were doing a cluster analysis with 4 clusters, we would do the PCA with 4 components. Okay, all right, so let's do a PCA and let's fit transform. And so you can see here it has gone from a 5 variable data set that's turned into an array, and now it is a 4 variable. And it's not like it just dropped off one of the variables. These are new variables that take into consideration the variability in these different variables. And it's not just clear as saying, okay, well, this is column 1 and 2 added together. Like, it's not like that. So what we're actually doing is linear algebra and taking matrices and combining and multiplying matrices to merge these together to create new ones. So that's where I'm going to wave my hands and say linear algebra to create these new variables that are functions of the original variables. All right, now let's look at the variability. So what we're going to do is we're going to do sum of PCA. That was the name that we gave it of the principal component analysis. And we want to call from that explained underscore variance underscore ratio. So the variance ratio says what percentage of the variability that was in the original data set is explained by this new condensed data set. Okay, so we look at this VR. And if we had 4 components, our VR here is 99.8%. So we went from 5 variables to 4. We still explain almost 100% of the variability in the data. So not a problem to go from 5 variables to 4 variables. As we said earlier, what we want to do is we want to make sure we're still explaining 90 to 95% of the variance to make sure that we're capturing the nuances of the data set. So let's take a look. Let's create this graph that you see here, this explained variance ratio graph, to see how many components we could have. So we're going to create a loop, and you're going to specify the different number of components you want to consider. So we're going to go 0 components, 1, 2, 3, 4. Now, you notice I have written here 5 plus 1. There are, in this data set, 5 variables. Okay, so what I want to do is, if you remember a range goes up to but not including. Well, I don't want to go up to but not including 5. I want to include 5. So just as a reminder to you, as you're coding, if we want to consider the full range all the way up to equivalent to the number of variables you stuck into this thing, then it should be the number of variables that you have in your original data set plus 1. 5 variables plus 1, so our range is going to be 0 up to, but not including 6, because then it will stop at 5. Okay, then we're going to say create this empty list called variable ratio, variance ratio, and then for num in nums, and if you want to put for I in nums, you remember this num here, whatever you put here is just a placeholder. You can call it whatever you want. Often coders do it like this, for num and nums, for color and colors, something like that. But if you come from, like me, an R background, it's probably always for I. The default in your loops is always just an I, but you can make whatever you want. So inside the loop, we're going to do a PCA. The number of components is going to be equal to, in whatever is listed here in nums, 0, 1, 2, 3, 4, 5. Then it's going to fit it on the scaled data. So remember, we have scaled our data here with our standard scaler. And then what we're going to do is we are going to append this information to that empty list. And the information we want to append is a sum using NumPy. So make sure you've installed NumPy here. And we want PCA.explained underscore variance ratio. So that's this PC explained variance ratio and the sum of it, okay? So it's the same thing we just did here with 4 components, and we're running through 0 through 5. So we do that. So there's this, there's that. And then we want to plot it. So matplotlib.pyplot as PLT. We want to plot on the x-axis the number of components, on the vertical axis that variance ratio. We'll call it explained variance ratio, and we'll mark these things with dots. We'll put a nice little grid in the back so that we can make it easier to see. So notice here, this 4, that was that 0.99 that got us here. So having the fifth component, having 5 full variables instead of our principal component analysis version, doesn't add anything. We were able to capture everything with 4. And as you look, if we go with 3 components instead, we're able to capture just more than 80%. You're looking for 90 to 95% in terms of the number of components to do your dimension reduction. Okay. If you choose the number of components down here, you're going to lose a lot of the variability that's in your data set in your reduced version, your dimension reduced version of your data set. Now, I did say that if we're doing cluster analysis or classification models, we want to pick the number of components that is the same as the number of clusters. And one of the reasons that we do that is because we only need as much variability as defines those 4 clusters or the 2 labels, or so all of the variability in the data may not be necessary for the number of clusters or the number of labels in your classification model that you have. So you can choose the number of components to match, but it's always a good idea to plot this out here so you can see how much of that variance you're losing there. All right, so let's try the survey. So data frame 2, this is the bargaining survey. Let's look at PCA related to that one. So if we were to reduce that one down, let's take a look. So we're going to use PCA. We're going to use standard scalar. We're going to use matplotlib.pyplot as PLT. So the difference between the one we just did and this one here is this is ordinal data. So let's take a bunch of variables, questions 6, 10, 11, 12, 13, 14, 15, 18, and 20. So these are all Likert scale questions. And we can use our principal component analysis and do some dimension reduction here. So here in this case, we have 3, 6, 9 different variables. And each of these variables is only a 5-point scale, right? So it's quite possible that a number of these questions are answered very much the same by each person. So for example, if someone strongly agrees on 15, maybe they strongly agree on 14, maybe they strongly agree on 13. If they strongly disagree on 15, they strongly disagree on 13 and 14. In which case, they're highly correlated to each other. We don't really need question 13, 14, and 15. With principal component analysis, it's looking at those relationships between these variables and saying, hey, the variability is already captured in some of these variables, or maybe it's this variable plus a little bit of the other variable. And so that's how we're able to reduce the dimensions. We don't necessarily need 9 variables. We need a new format of these variables that simplifies it down. So we're going to create a new table here. We'll call it Likert, because these are all the Likert scale questions that are in that data frame. And we're going to we can make a copy here of data frame 2 that's just these Likert scale questions. And we make a copy because the next step here is we're going to drop all the empty ones. So we're going to drop all the ones that have missing information like this that you see here. And so we don't want that to happen from the main table. We want that to happen from our new table. So we don't want this to just be a link to a part of the original. We want it to be its own table itself. So take data frame 2, take all these variables, make a copy, call it a new table called df Likert, and then take df Likert and drop the NAs. Okay. Now, here, this is a standard scalar. Because these are all Likert 5 scale questions, you don't technically need to do standard scalar. I put it here because it's just good practice that if you have data that needs to be standardized based on the methods that you're using, you should just always remember to have that so that you don't forget the one time that you have data that should be standardized and you forgot to do it for that method. So I put it in here, but because this is ordinal data and it's all the same 5-point Likert scale, you don't really need it. Okay, but let's just do it. Here we go. All right, then I have 9 variables. And so I'm going to go through a range from 0 to 9 plus 1 so that I make sure 9 is included. And then I'm going to do that same loop again. So I'm going to create an empty list for my explained variance ratio. And for num and nuns, remember this is just a placeholder for whatever you're going to put here. And then we're going to do the PCA. We're going to fit it to our scale data. And then we're going to append that PCA.explained variance ratio so that we can see how many different components we can get this down to. All right, so we did our nums. We'll do our loop. We'll plot it just like we did with the previous one. And so when we look at this particular data set here, what you can see is that with 6 components, we're getting to just around that 90%. And so instead of 9 variables, there's a lot of redundancy in those variables. We can actually get it down to 6 principal components that are just revised versions of those 9 variables as they're condensed into new versions. Okay, so we could use this simplified approach. Now, we don't need to do this PCA for either one of those data sets. Those data sets are small. We were fine running 9 variables or 5 variables, right? No big deal. Let's try a much bigger data set. So this is where principal component analysis comes in. We have much bigger data sets. So from sklearn.datasets, we're going to import fetch_openml. Remember when we were in the Google Cloud, there was a number of data sets under ML. These data sets are available in that Google Cloud. They're also available online. So there's a whole set of data sets through something called OpenML that are machine learning data sets to help you learn how to do machine learning before you build your own data sets. And so we want to call one of those. So we're going to import fetch_openml. And we are going to find the MNIST data set. So we're going to do fetch openml. We're going to call the MNIST 784 version equals 1 data set. This is a big data set. It can be kind of slow to load. So when we get this data set open, what this data set is, while it's running in the background, is this data set is 10,000 handwritten numbers, like this one that you can see here. There are 10,000 of them. Now, each picture is 784 squares. So you'll notice some of these portions of this picture, the square has no information, and then other squares are going to be a number between 0 and 254, depending on how dark that pixel, that square is. Okay, so we have a huge data set. There are 784 variables. There are 10,000 rows of data. Okay, so we are going to call this X. We're going to say X equals MNIST data. So this is just because the format that that's in. We're going to label it X, okay? So we're going to call that X, and we're actually going to just take X and we're going to take 10,000. Okay. Now, from this, what we're going to do is we're going to do different versions of PCA because it is such a large data set. And so we're going to do things like incremental PCA because the data set is so large. So we're going to add the data in batches, and then we're going to try to consolidate the 784 variables down using our principal component analysis to a key couple variables that cover all the variability in these images. And then we can use that for things like image recognition.